Good afternoon, everybody. So this is the third lecture on thermodynamics, and in order to start the lecture, I would like to tell a few more words about thermodynamic potentials. So the thermodynamic potentials were introduced at the last lecture. We saw it is a quantity which is measured in units of energy, and this is a quantity which is at minimum if thermodynamic system is in thermodynamic equilibrium. We have introduced at least 4 thermodynamic potentials, and you may ask yourself, why do we need so many of them, and why do we need the concept of thermodynamic potential at all? Let me start with the simplest example of thermodynamic potential, internal energy. If you write first law of thermodynamics, and try to specify the case. Well, imagine that we are talking about internal energy of gas. Then internal energy of gas can be changed by performing work on the gas or by supplying to the gas some heat Q. So we use this expression for the work performed on the gas, which we gave already in lecture number 1. And write expression like this. Then, according to the definition of entropy, if we talk about reversible process, Q can be defined as a product of temperature and differential of entropy. So then eventually it results an equation like this. So this is the first law of thermodynamics for the case of gas. As you can see here, internal energy is a function of volume and entropy. If volume and entropy do not change, it means that the internal energy doesn't change as well. But do not forget that this is the case only if you talk about reversible processes. If process is irreversible, or if we talk about a general case where a process can be either reversible or irreversible, then this differential of Q would be either less than this product temperature and differential of entropy, or equal, where equality is valid for the case of the reversible process. So if you take this inequality, then you can write equation like this, from where you see that whatever happens in this system, if volume and entropy do not change, internal energy either doesn't change or the changes are negative, from where it follows that if volume and entropy are constant, internal energy should be at minimum. Because if volume and entropy are constant, whatever else happens in the system, we don't know what, internal energy either doesn't change or the changes are negative. So it means that if you're talking about thermodynamic equilibrium, internal energy should be at minimum. You can have a very clear analogy of this fact. So if you imagine a very hilly environment somewhere like this, and you're looking for the most stable position, for instance, of a ball. So you can see here, as soon as ball gets into this very deep well, chance to get out of this well is very small, so practically zero. because in this well, potential energy of the ball, or you can say internal energy of the ball, is at minimum. It's exactly what I want to say with this example. In thermodynamics, thermodynamic equilibrium corresponds to the case in which internal energy is at minimum. So thermodynamic system tries to minimize its internal energy, and in this way it searches for the thermodynamic equilibrium. So as you can see here, internal energy can be then used as analogy of the potential energy in mechanics. Internal energy would be then analogy of potential energy in thermodynamics. So for this reason, we will call internal energy thermodynamic potential. So it's something that tries to reach minimum and in this way establish thermodynamic equilibrium of the system. So we will call internal energy thermodynamic potential, but next to internal energies we have other thermodynamic potentials. And as we showed last lecture, if you look at function defined like this, it is also measured in units of energy, and it is also at minimum when system is at thermodynamic equilibrium. In order to see it, you have to differentiate this expression. Then you substitute this expression into here, and you will find that if you are talking about reversible process, then differential of this function f would be equal to expression like this. And if you are talking about a general case, then it would become inequality. It means that if we now fix volume and temperature, if volume and temperature are constant, then if anything else happens in the system, we don't know what, this quantity can only change to smaller values or it doesn't change at all. It means that if you are talking about thermodynamic equilibrium in which quantities which describe the state of the system do not change, this quantity f must be at minimum. So it satisfies the definition of thermodynamic potential. We can also use this as a thermodynamic potential the same for the very same purpose as we use internal energy. But what is the difference between internal energy and f? The difference is in the variables. If here I used volume and temperature as two variables, here I use volume and entropy as two variables. What happens here? If you look at the ideal gas can be described by pressure, volume, entropy, and temperature. But as a matter of fact, out of these four variables, only two of them are mutually independent, and the rest will depend on these two. Meaning that if you know volume and entropy, you can calculate pressure. If you know volume and entropy, you can calculate temperature. If you know temperature and pressure, you can calculate volume, and if you know temperature and pressure, you can calculate entropy, but it is only possible if the system is in thermodynamic equilibrium. Don't forget about it. And we have so many parameters that can in principle describe the state of the system, and we always use just two of them. Well, depending on the pairs of parameters that you use, you can write either one type of thermodynamic potentials or different type of thermodynamic potentials, or even third type of thermodynamic potentials. Each of the thermodynamic potentials basically expresses internal energy in terms of two parameters that you choose. If you talk about internal energy in the classical understanding of this term, then in this case internal energy depends on volume and entropy. But you can express internal energy in terms of volume and temperature, and then you will get basically also energy, but written in different coordinate systems. So what I've done by transferring from by coming from this quantity to this quantity, I just changed coordinate system. And then depending on the coordinate system that you use, you can use different thermodynamic potentials. You will see that there are thermodynamic potentials which are called enthalpy, and enthalpy uses entropy and pressure as two variables, or Gibbs function, and Gibbs function uses temperature and pressure as two variables. So far we used internal energy, another example, just the main example of thermodynamic potentials, and internal energy uses entropy and volume as two variables, and also I use quantity F, which is called Helmholtz energy or sometimes free energy, and it uses volume and temperature as two variables. As you can see, thermodynamic potential is just an expression for energy, which should minimize if the system is at thermodynamic equilibrium, and the difference between one thermodynamic potential and another thermodynamic potential is just a set of variables that you choose. And now we are ready to go to the next topic in the course, and this is basically showing how to use thermodynamics as method in physics, how to use thermodynamics as a method in research. In particular, I'm pretty much sure you hardly heard about effects like magnetocaloric effect or thermoelectricity or thermomechanics, thermomechanic effects. You haven't had this, you haven't had paragraphs on these subjects in your curriculum yet, and even you maybe even do not understand what these effects are about. Using thermodynamics, I will show you that we can explore these effects. Let me show you the main principle that I'm going to use. Here I try to summarize all the topics that you will that you have lectures on in university educational program. It is you normally start with mechanics, then presently you follow course on electricity and magnetism, and you can find a lot of links between mechanics and electricity and mechanics and magnetism. And the link, for instance, between mechanics and magnetism is called piezomagnetism. So these are phenomena which are at the interface of magnetism and mechanics. That's when you act on the system mechanically and you change magnetic properties of it. Or you can act on the system electrically and you change magnetic properties of it or mechanic properties of the system. But on this map of all physics, thermodynamics would be in the central position. This is more or less my goal for today, and to show you that although you know nothing about piezomagnetism, for instance, or magnetocaloric effects, using the tricks of thermodynamics, you can study these phenomena. In the lecture, I will use two mathematical tricks. One is called reciprocal theorem, and it is formulated in the following way. So if you have variables x, y, and z, such that you can write an equation this equation can be written in a different form. Several expressions can be defined, can be derived from this for this function, and one is reciprocal theorem. And another one is reciprocity theorem. So the same theorem can be written slightly different way. Okay, so this is called reciprocity. Let's look at the internal energy for the case when we're talking about ideal gas, or just gas, doesn't matter if it is ideal or not. We write first law of thermodynamics. Then we play with this law a little bit. We take derivative of the internal energy with respect to volume, for instance, while keeping entropy fixed. And this derivative is equal to pressure with sign minus. Then we take another derivative of internal energy, and in this case with respect to entropy, while keeping volume fixed. And in this case, we get temperature as a result. If you now calculate second derivative, in this case, we'll get result like this. And if we calculate second derivative in this case, we'll get this derivative. Well, you can ask yourself whether the result of differentiation matters in these two cases. Can we claim that the order of differentiation affects the final result? Well, what does it mean in physics if the second derivative doesn't depend on the order of differentiation, like in this case? So we can discuss details at the questions hour, but the statement I would like to make: in physics, if the order of differentiation doesn't affect the second derivative, it means that in this particular case, it doesn't matter whether you first change volume and then entropy, or you first change entropy and then volume, internal energy changes in the very same way. And if this equality is valid, we can now derive an expression This expression describes behavior of gas, and this is called Maxwell relation. So something new that we can learn about behavior of gas, something that we didn't expect to see before we started perform all these differentiations. So this is a new law which can be used in studying physics of gases. So something that follows from thermodynamics. We have derived new law, and there is a nice thing that we can derive many of laws like this, using the very same trick. Now, after I looked at the internal energy as thermodynamic potential, maybe I should look at different thermodynamic potentials which operate with different variables. For instance, I look now at the thermodynamic potential, which is equal to this expression. So after I differentiate this thermodynamic potential, which is called Gibbs function, and put here first law of thermodynamics for the case of reversible process, you will find that the differential of this function is equal to so as I have just explained previously, what we have done now by coming from internal energy to this differential potential, to this thermodynamic potential, we basically changed set of variables. From volume and entropy, we went to pressure and temperature. And now we use the very same trick. We calculate first derivative of this thermodynamic potential. We calculate another third derivative of the very same thermodynamic potential. Afterwards, we assume that the order of differentiation doesn't affect the result. Meaning that it doesn't matter whether you first change pressure and then temperature, or first temperature then pressure, you will arrive to the state with the very same value of thermodynamic potential. And from this, we can derive another Maxwell relation which is also a new law, something we haven't, something we were not aware before this lecture, but using simply first law of thermodynamics and playing with the second derivative, assuming that the order of differentiation doesn't affect the second derivative of the thermodynamic potential, we could derive an expression like this. It's also called Maxwell relation. So depending on the thermodynamic potential that you take, you can derive many Maxwell relations, and you can, for instance, relate such a quantity as derivative of entropy with respect to pressure. You may know nothing about behavior of entropy because there is no device that measures entropy. But using this Maxwell relation, you can calculate that entropy changes with this when you change pressure at fixed temperature in the very same way as volume changes when you change temperature and keep pressure constant. By the way, using theorem I showed just at the beginning of the lecture, you can write the very same expression slightly differently. In the following form. And this is also new law. So with the help of thermodynamic potentials, we get very powerful tool in physics, we can derive many Maxwell relations. And a general approach to derive Maxwell relations is very simple. You just choose a set of variables that you need. In this case, set of variables, for instance, is pressure and temperature. It's because pressure and temperature also seen here as fixed parameters, by the way. So that the pressure and temperature being variables in this case allow you to find the laws about behavior of entropy and volume. And there is a very simple way to check if your Maxwell relation, if the Maxwell relation that you have just derived is a correct relation, is to look at the crosses in Maxwell relation. And if you look here and here, you will notice that where the product of these quantities is measured in units of energy. Pressure times volume is energy. Entropy times temperature is energy. If you look at the differential here, then the quantity which is with respect to which we differentiate left part, this quantity shows up as a constant on the right part and other way around. And the sign, you will notice also after you derive several Maxwell relations that the sign is positive if pressure and temperature appear on the same side. If they appear on different sides of Maxwell relations, somewhere either on the left or on the right, you should have minus sign. And using different thermodynamic potentials, using the trick of this second derivative, we can derive many Maxwell relations. So in this particular case, 4. And as I said, this is straightforward approach. And you just have to choose right set of variables and repeat the very same trick. Well, let me come with an example how to construct a thermodynamic potential that you need. Well, if you want to have a specific example, we have to formulate specific physical problem. So in my particular case, imagine that I'm talking about a wire under tension. Wire experiences force F, and this force F changes the length of the wire. On the top of this, also wire is under pressure, and the pressure can change volume of the wire. And I would like to construct thermodynamic potential which uses temperature, length, and pressure as 3 variables. In order to derive correct thermodynamic potential, in order to construct correct thermodynamic potential that we need before we start deriving Maxwell relations with these variables, we have to write first law of thermodynamics. Normally, first law of thermodynamics contains 2 variables. Normally, it's because we used only 2 variables so far. I will explain you why. If you're talking about reversible processes, we can use this equality. Previously, when we used only pressure as an external stimulus, we indeed had only one quantity changing, volume. But now I'm using both pressure and force as external stimuli. So then we have here an additional term that contributes to the internal energy, an additional term that performs work on the system. That's why instead of 2 variables, we have 3 variables in the first law of thermodynamics. And these variables are volume, entropy, and length. So what we have now, volume, entropy, and length as variables. Instead of volume, we must have pressure as a variable, and instead of entropy, we must have temperature as a variable. The fact that we have length as a variable fits to the requirements of the problem. So what we have to do in order to get this substitution of variables required for construction of the desired thermodynamic potential, we have to take internal energy and for the substitution of S to T, we subtract this term, and for substitution of V to P, we add a term like this. If you don't believe me, you simply have to write differential put here an expression for the internal energy and obtain the final result. So differential, this change of F can be obtained either by change in pressure or by change in temperature or by change in length. So practically we arrive to a function which measures energy or internal energy of the system in this coordinate system: temperature, length, and pressure. So in this way you construct right thermodynamic potentials. Now let me come with a specific example. Surface tension, for instance. So the surface tension is an elastic tendency of a fluid surface which makes it acquire the least surface area possible. So that, for instance, insects do not sink in water, they can jump over water. And I have a very fundamental question here. How does surface tension depend on temperature? I know nothing about nature of liquids. I will consider. I will just use thermodynamics to answer this question. And I will use three steps. Define the set of required variables in this case, construct thermodynamic potential, and derive Maxwell relation. First, we realize that work performed by the thermodynamic system in this case is this coefficient gamma, which is defined as surface tension, and the change of surface area A. The goal of our derivation is to find temperature dependence or something about temperature dependence of gamma. Yeah. We define the set of variables here. The variable is obviously temperature and apparently surface area. We construct thermodynamic potential. We start with internal energy. For the case of reversible process, it is temperature times change of entropy plus gamma, the surface tension, times change in surface area. Then we perform substitution of variables by subtracting term Ts, because what we want is to have, instead of entropy as a variable, we want to have temperature as a variable. So we do this substitution and we get the required result, and finally we just have to differentiate this function phi that we have defined twice and use the fact that order of differentiation doesn't affect the final result, so that eventually we arrive to the expression like this. Entropy, derivative of entropy with respect to surface area at fixed temperature is equal to derivative of surface tension with respect to temperature at fixed surface area. and with negative sign. Here we can also use the slightly different expression, because you may not like a derivative like this in your expression, because again there is no device to measure entropy. So you can say this expression tells me nothing because I don't know how entropy behaves as a function of surface area. No problem. You can use the definition of entropy for the case of reversible process and put this expression there. Basically, it is heat which is exchanged between the system and the environment when we change surface area at fixed temperature. So that the final expression is like this, and this is the law that predicts the behavior of surface tension as a function of temperature. The law we have just derived together, knowing nothing about nature of the liquids, just purely from first law of thermodynamics and definition of entropy, and using the fact that order of differentiation in the second derivative doesn't affect result of the differentiation if you talk about thermodynamic potentials. Another example, magnetocaloric effect. So magnetocaloric effect is interdependence of thermal and magnetic properties of medium. For instance, when the magnetization is changed isothermally, heat is exchanged with the surroundings. And if the change of the magnetization is performed under adiabatic conditions, the temperature changes. So it means that if you succeed to change magnetization of medium by applying magnetic field, for instance, you are able to change temperature of the medium. So this principle is used, for instance, in fridges. So you can see here fridge for wine, which is free of any vibrations. Apparently it's very important in that case. And this fridge for wine, free of vibrations, employs magnetocaloric effect. So the fact that you can change temperature of the medium, apply a magnetic field. How can external magnetic field change the temperature? Again, we know nothing about magnetocaloric effect. We just want to figure out how is it possible that magnetic field, apply magnetic field with vary temperature of the medium. Again, we write the first law of thermodynamics. We notice that the work performed on the system is now equal to mu0 fundamental constant, h magnetic field, and the change in magnetic moment. So this expression we used already in the previous lecture. We want to describe magnetocaloric effect using such set of variables as temperature and magnetic field. So these are our variables. We write the required thermodynamic potential for this case, and for the required thermodynamic potential we need to substitute variables. Instead of entropy we will use temperature, instead of magnetic moment we will use, or magnetization, m small, we will use magnetic field. Then you can see that this required substitution of variables is achieved by subtracting these two terms, like product of temperature and entropy and product of fundamental constant mu0, magnetic field and magnetization. Then after that we derive Maxwell relations using second derivative of this function, and we arrive to the expression that entropy changes while changing magnetic field at constant temperature in the very same way as magnetization changes while changing temperature at fixed magnetic field. So finally, we would like to answer the question that we had in the first place. How can external magnetic field change temperature? For this, we use theorem, which I showed at the beginning of the lecture. I also notice that this expression, this derivative, is heat capacity measured at constant magnetic field divided by temperature. Why? Because if you look at the first lecture, then heat capacity measured at constant magnetic field is defined like this. So we basically put this expression and we use this expression in the case of Maxwell relation we have just derived and arrive to the final expression that in principle temperature can be changed by magnetic field if magnetization in a medium depends on temperature. If this derivative is not zero, and this derivative is not zero, we showed this at the previous lecture while we derived the behavior of the magnetization as a function of temperature. We showed that this magnetization decreases as temperature increases. So from here, from this law, you can predict how magnetic field can change temperature of the medium, because this law is known, and knowing heat capacity, we can find this derivative. And you can also derive Maxwell relations for such an effect as a thermoelectricity when, for instance, we use heat to produce electricity. So it's by many people seen as very useful effect to study, because as you can see, we are using electricity everywhere. We waste in most of cases most of electricity is wasted to heat, and would be nice to pick up this heat and produce again electricity out of it. So that's why we want to calculate, is it possible to induce electric polarization as a function of temperature, and then we can repeat derivation of Maxwell relations. In this case, we start with slightly different thermodynamic potential, where instead of magnetic field and magnetization, we will operate with electric polarization and electric field. The only difference with the previous case would be that work performed on the system now defined differently, because if you look at the textbooks, work performed on the system is defined as the electric field times change of the electric polarization caused by this electric field in a medium. You just take this expression and then you repeat the very same steps we did. You write first law of thermodynamics. For the case of reversible process, you notice that instead of S as a variable, you want to use temperature, instead of P as a variable, you better use electric field. And you can derive right thermodynamic potential and derive Maxwell relations in this case, which will give you the required Maxwell relation. So the take-home message for today, I hope I was able to convince you that thermodynamics allows one to reveal and describe physical phenomena using Maxwell relations without specifying microscopic mechanism responsible for those phenomena. We treated mechanical phenomena, thermoelectric phenomena, and the magnetic caloric phenomena. Without knowing physics of all these effects, we were able to derive laws. And with all this, I would like to make once again the statement that I did at the very first lecture. Thermodynamics is a powerful and universal tool in physics. Thank you very much.